there. All right, today's lecture, we are going to be talking about atoms, talking about the beginning of the atomic theory and how this amazing microscopic world came to be discovered before we could even see in microscopic forms to this level. This is a fascinating subject because you can really see how science can start to parse out things that we can't even see. That we can come up with these theories that we then use and come up with experiments for those theories so that we can see whether there's a truth or not about the world that we can't even see. It's kind of like a black box. Something inside that you don't know what it is. You have to kind of do a bunch of little things to figure out what's in there. That's what the atom is. And today's lecture is a lot of fun because we kind of go through the exploration of how that came to be, at least at the start of it. We're going to see a lot more of it in further lectures. So this is an image of an atom or atoms. This is a scanning tunneling microscope. Now, when I was in college, they still hadn't even come up with this technology. They had scanning microscopes, scanning electron microscopes, but they hadn't come up with the ability to see atoms yet. And so really what we're looking at here is kind of like the shape that the electric field is creating in that atom. So we can see kind of multiple atoms here. But it's just so cool that we now have technology that can dive down into the actual size of an atom. So it's a lot of fun. So today we're going to talk about the conservation of mass, and give examples of the law of definite proportions and multiple proportions. And then we're going to talk about Dalton's atomic theory. We're going to be able to list 5 different principles and identify which ones are no longer valid. So we'll say, yes, I can explain conservation of mass. That's for our criteria for success. And also the law of definite proportions and multiple proportions. Those are a little bit foggy. They're kind of similar to each other. So some students have a little bit of trouble distinguishing those, but we'll go through those. And then talk about which parts of Dalton's theory no longer hold true. Now this is just kind of a short history of some of the scientists that were involved in coming up with the atomic theory. Going all the way back to Democritus in 400 BC. There was another philosopher by the name of Leucippus who was supposed to be Democritus's mentor, basically. And they say that he actually might have come up with this, but some people are, they still dispute that. They believe he's real, but some scientists or some people say that he's not, wasn't actually real. So anyway, we don't know for sure. But Democritus coined the term atom, atom, right? Meaning without, and then tom meaning cut. So you can't cut it. That's the idea here. And then we've got people like Dalton, Thomson, Rutherford, Bohr, Millikan, de Broglie, Schrödinger, and I should say Schrödinger with an R, and then Chadwick. So we're going to go in, we're going to talk really just about Dalton today a little bit, and some of the scientists that were also helping him come up with his idea. And though they're not even on here, we're going to talk about Proust, we're going to talk about Lavoisier, and then Dalton today, and then we'll get to some of these others as we get going. History and chemistry are so tightly connected, and it's a lot of fun to connect those two in our lectures. And so we're going to be doing that a lot here lately. All right, there was a guy by the name of Mikhail Lomonosov who actually came up with this idea in 1748 of the law of conservation of mass. But really, we get a lot of the credit to this guy, Lavoisier. Okay, Lavoisier was considered the father of modern chemistry. He died at the age of 50 from Madame Guillotine. He had his head chopped off. Oh, anyway, he stated in 1774, quite a bit after Mikhail, right, that nothing was lost, nothing was created, everything is transformed. And he did this experiment. One of the experiments he did, which was so cool, he took basically a long lever, right, and kind of like a balance. And he did a chemical experiment in this one where he was burning something, and he wanted to see, well, if it's burning something, that thing disappears, therefore it should now be lighter, right? Well, it didn't get lighter. They stayed the same weight, okay? The balance he had here and the thing that was in an enclosed container. He kept all those gases that were burning away, and people before it thought, oh, well, they're burning away, so they're gone. But he was able to show that, no, it didn't disappear. And so that was Lavoisier's experiment, a lot of fun. It's a really interesting story about him, too. He was killed for political reasons. And although this is apocryphal, they don't think it was probably actually true. It says, on the appeal to spare his life, so he could do more experiments because he was 50, right? He has more science experiments to do. The judge stated, the republic needs neither scholars nor chemists. The course of justice cannot be delayed. All right. I mean, that's kind of sad. What else could he have done, if he'd actually been able to continue doing his work? He did a lot of really interesting experiments and helped us a lot. Came up with things like helping us with our nomenclature. He came up with the idea right before he was, executed, helping us to come up with the metric system. Did a whole bunch of great things. But anyway, he was exonerated 3 years after his death. They said it was all lies. He was basically convicted for maybe giving money to the enemies and then for putting water in tobacco to make extra profit, which he didn't do. He was actually trying to go against it. Anyway, fascinating story. You can look into it if you want to. Neat guy. All right. Law of conservation of mass. The idea here behind the law of conservation of mass, again, is that balance thing. Like, you're going to rearrange things, but you are not going to lose anything. You're not going to destroy matter, okay? So matter can be transformed, but it's not going to be destroyed. Okay, so that's what we're looking at here. And so we've got sulfur and oxygen combining to form sulfur dioxide. We've got some mercury and oxygen coming apart into the separate mercury and oxygen parts, where here it's mercury oxide, right? Here we've got the rearrangement of atoms where we've got this hydrogen carbonate, and it basically separates out into water and carbon dioxide. So this is the law of conservation of mass. You'll notice that you have the same number of particles on this side of the reaction as that side, on this side as that side, on this side as that side. So the number of particles, the number of atoms doesn't change in the chemical reaction. That's an important concept to keep in mind. Okay, then we got law of definite proportions. Now this guy by the name of Joseph Proust that really kind of came up with this concept, basically saying that chemical compounds contain the same elements in the same proportions regardless of the size of the sample or the source of the compound. In other words, no matter where you get the water, let's say we've got some water and we're up on Mars. Water on Mars, that ice that they have on Mars, that's the same water that we have here on Earth, okay? The water in the bottle is the same as the water that comes out of the faucet. Water is water. It's always H2O. It's going to have the same proportions, definite proportions. That's the idea behind the law of definite proportions, okay? Now, again, another example, the proportions by mass, okay? So whether or not we have 31 grams of water or 8 grams of water, you're going to end up having an 88.81% of oxygen, 11.19% of hydrogen, same proportions. Okay, then we have the, I'll give you a little example here. Sample for, chance for you to try it. So your turn, pause it, see what you get. Okay, sample of calcium chloride, contains 40 grams of calcium, 70 grams of chlorine. If another sample contains 42 grams of chlorine, how many grams of calcium does it contain? Hopefully you just did a real quick ratio, all right, where you could figure out the ratio that you had before and then take the 42 and then come up with a new ratio. So 40 is to 70 as X is to 42, therefore 24 grams of chlorine. So here we're practicing that law of definite proportions, right? You're going to always have the same amount of calcium to chlorine as long as you still have calcium chloride. If it's something different, then you might have different proportions. But if it's calcium chloride, same thing, okay? Now, let's look at the law of multiple proportions. Now, this was one that John Dalton actually came up with. We're going to go through Dalton's theory, his atomic theory here in a bit. And his theory is kind of like a compilation of a few different people's work. But this is one that he actually came up with. 1804 is when he came up with it. When two elements combine to form two or more compounds, the mass of one that combines with the given mass of the other is in a ratio of small whole numbers. Okay, you're like, what? That sounds kind of confusing, Powers. Okay. Basically, you can't have part of an atom. Now, this might seem like, well, duh. But remember, these guys were coming up with this before they even knew what an atom was. We had not yet come up with an atom, and yet they're trying to figure out, what's oxygen? Well, oxygen's made up of 2 atoms of O, right? But they don't even know what an atom is. So how do they figure this stuff out? They did some pretty amazing work to figure it out. But the idea here is, again, you can't have part of an atom. And so if I've got any compound that has nitrogen and oxygen in it, it's always going to be a whole number ratio of nitrogens and oxygens, okay? Whether it's an NO, a 1-to-1 ratio, or an NO2, where it's a 1-to-2 ratio. You're always going to get this whole number ratio of atoms in combinations when they combine. You don't have parts of atoms, okay? So you can also say the same for H2O, water, and H2O2, hydrogen peroxide, right? So, oops. I might have given you an answer. Which of the following sets of compounds are examples of the law of multiple proportions? Okay, woohoo, yeah. Now, are SO2 and H2SO4, are they the same thing? No, because look, there's an H here, but there wasn't an H on this one, okay? So remember, this has to do with things that have the same elements in them. CO2 and H2O, no, okay? So that first one was, and the other ones aren't. You could do CO and CO2, but you're not going to say CO2 and H2O are examples of multiple proportions because they don't have the same elements in them, okay? All right, so Dalton's atomic theory. Now, Dalton was a really interesting guy. This guy became a school teacher at the age of 12, okay? So here's a pretty smart guy. But one of the things that I love about Dalton is that he did a great job of synthesizing concepts, okay? Now, there are certain people that are great inventors. And then there are other people who might take just ideas that are already out in the world and they put them together in a way that some of us have never even thought of before. And all of a sudden they've revolutionized the world because they compiled other people's information into one, congruent, fluid thought. And that's kind of the way I think of a Dalton. Because again, he came up with the law of multiple proportions, but for the most part, everything he came up with was somebody else's work. But he brought it all together, came up with this atomic theory that we now still use today, even though some parts of it aren't exactly true anymore. We still use this to this day, which is so cool. So all matter is composed of extremely small particles called atoms. All right, so that's the first one. Now you'll notice I have little asterisks by some of these. And if I have an asterisk by it, that means that it's not really true anymore, okay? At least not completely. There are definitely some things that we can have exceptions to. So for instance, although we now, yes, still believe that matter is composed of atoms, we also have particles that are smaller than atoms. So you could kind of argue, well, yeah, but there is an electron, and an electron is matter, and it's also not really an atom, right? So it's an electron, not an atom, but yet it still matters. So yeah, so one is true, but not anymore. Atoms of a given element identical in size, mass, proportions. Atoms of different elements, different size, mass, and other properties. So for instance, zinc is not going to be the same as lead, okay? Those two things are different. And if it is zinc and zinc, it doesn't matter where you got the zinc is identical to zinc, okay? It's going to have the same properties no matter where you get it from, but it's not going to be the same as lead. Atoms cannot be subdivided, created, or destroyed. Yeah, okay, this is one now that we'd have to say, well, because of nuclear reactions, yeah, we can actually divide things, right? and sometimes this happens naturally, right? Radioactivity. Atoms are subdividing into smaller pieces even through natural processes. So atoms, yes, they can be subdivided now. However, are they created or destroyed? Well, the matter isn't created or destroyed, but the atom might be changing, right? And so you could say, yeah, well, in a nuclear reaction, for instance, a fission reaction, you've got the matter turning into energy. Fusion, you've got energy turning into matter. Lots of cool stuff there. Did I say that right? Yeah. I don't know. Yeah. Anyway, number 4, atoms of different elements combined in simple whole number ratios to form chemical compounds. So this is just an idea like sodium and chlorine come together to form sodium chloride, right? So these things are combining to make compounds from different elements, okay? And then in chemical reactions, atoms are combined, separated, or rearranged. So again, these things seem really simple, but this is, again, before they even understood what an atom was. And so, what's the difference between this, the stuff, I have this rock, and then I pour some acid on it, and all of a sudden it's bubbling. Like, what's happening there? Is it magic? Or is it maybe a place in some ways where things are combining and separating and rearranging? And so, oh, wow, maybe I had this rock and now it's turning into something else. It's turning into a gas. How does a rock turn into gas, right? Some of these things just seem like completely foreign ideas to these scientists in the beginning. All right, so Dalton's model of the atom. I just kind of want to talk about each of these different models and what they would be like. If I were looking at Dalton's model of the atom, this is just a solid sphere, okay? He looked at the atom as a solid sphere, kind of like a billiard ball. So you can think of the billiard ball model of the atom. Okay, Dalton just thought, boom, chunk, all right? We're going to go on to see some other ideas about the models of the atoms here in a bit. Okay, so which components of Dalton's atomic theory have now been shown to be false? Okay, we talked about those. Those are the ones in the asterisk, so maybe go back through and review those here in a second. And now let's try to see if you can figure out which ones. Oh, well, I've given you the answer, so I bet you can't figure it out. Okay. These were supposed to, come in on the clicker, but I guess not. There is no difference between copper found in an ancient Mayan necklace and the copper wire freshly made from ore. That's Dalton's second principle, right, in his atomic theory. And again, that's just saying, elements are the same as other elements no matter where you find them. Formula for ethanol is C2H6O4. H6O, sorry. That's the fourth because it's saying that these things are combined, right, in simple whole number ratios. We don't have a half here. Everything is in a whole here, okay? Zinc is softer than iron, reacts more readily with acid than iron does. Okay, so it has different properties. That's the second, right? Elements are the same if they're the same. Zinc is zinc, but zinc is not lead, okay? Or zinc is not iron in this case. Matter can never really be thrown away. One reason the cycling is important. That's the third. Cannot create matter, you cannot destroy matter, okay? So we got to make sure that we're taking care of our world here. When methane burns, it combines with oxygen in the air to form molecules of water and carbon dioxide. That's the fourth, right? But it's also the fifth. It's combining, that's the fifth part. And it's fourth, they're in whole number ratios. They're kind of showing ratios there too. So, yeah, glad I gave you the answers there. Just make sure you can do that on your own. Why are the following considered laws? We've got the law of conservation of mass, definite proportions, and multiple proportions. Remember that laws describe what, okay? They're explaining what. And so here we're just saying, yeah, these things are the way we see things, that things are always combining in multiple ratio, or in whole number ratios, for instance. And so these are all whats, okay? But then his theory is a why. His theory is trying to explain, the why of the atom, the how of the atom. Why is this thing doing the things it does? Because it has these various different properties, then it can describe why the atom does the things that it does. And so, and again, remember, that was a theory. Theories have been shown to be true over and over and over again. Now, granted, there's definitely been a lot of things that have changed since that original time, but theories are true, right? And even his theory is true to this day, even though some of the parts of it, have been shown to be changeable to a degree. We've had to modify that theory. And theories can be modified. Laws can be modified. When we find new evidence as scientists, we change and we explain it in a new way. And so if we wanted to, do a modern atomic theory, we'd probably say a couple things differently. This is still Dalton's atomic theory, so we can tell you all the things that are not right about it anymore. But theory explains why, okay? All right, well, let's see if we can go over what we've learned. We can now explain the conservation of mass and give examples of definite proportions, multiple proportions, right? Definite proportion, can you give me an example? Water's the same as water, no matter where you get it. Multiple proportions. Water and hydrogen peroxide are both in whole number ratios, okay? And then conservation of mass, yeah, you can do that one. List 5 principles of Dalton's atomic theory. Identify which are no longer true. Yeah, we've done that. You got this. Okay, it was fun. We learned a little bit about Dalton's theory, learned a lot about atoms, and a little bit about the history. We're going to be hitting history later on, even more. Why is history important? Well, as we just explore the transformation that these scientists went through and the things that they were able to do, we can see maybe a little bit of what we might be able to do and what our future is going to look like. Like you someday might be one of those scientists who is digging into a black box and trying to understand the concept that you can't see, and yet you will revolutionize the world because you dug into it with scientific method. Okay, and you're going to stand on the backs of giants, right? You're going to stand on those who have come before you, have done all that work as well. We wrote it down. Remember, in science, we got to write this stuff down because we want to practice passing that on to next generations, right? And so we can stand on the backs of giants because we're here at Dublin learning what we're supposed to be learning, right? Getting better and better. You have a great day. That was fun.